morning, students. So in earlier class we discussed the approximate estimation of endurance limit. So as well as in previous classes we have seen the SN curve diagram. In that we observed, so there is the two regions we identified that. So that is a low cycle fatigue and high cycle fatigue. So that is the machine component subjected to up to 10/3 number of cycles it is sustained, and it is going to fail below this region. We call it as a component, so comes under the low cycle fatigue. For those components, we can simply apply the methods or theories or criteria we are having for the static loads. So those can be applied to these components, but with the maximum factor of safety. But coming to the machine component that fall under the region of high cycle fatigue, that is a machine components above the 1000 number of cycles and can operate infinite number of cycles, we require different criteria, so or different theories so that need to identify or we need to apply, so in order to avoid the fatigue failure. So in today's class, so let us discuss what are the criteria we are having that the machine components are subjected to fluctuating stresses, and that is we avoid the fatigue failure, that is by means of the strength, endurance strength. Based upon the endurance strength, we can going to design these components using the following criteria that we discuss here. Natural working conditions. But coming to the, another method, one is that is another method. So in order to find the endurance strength of single material, so we need to conduct a series of tests so that we can get the set of values. That is what we have seen in the fatigue test values. So using that set of values, we plotted a graph of SN curve of after 10⁶ infinite number of cycles we consider as an endurance limit. But for each and every material, so if you want to conduct a test, it will takes a greater time as well as money incurred in that, so that it will take a long period of time to conduct a fatigue test for each component to find out the endurance limit. So for that reason, there is an appropriate estimation can be formed using the proportionate values with respect of relation can be given with respect of the ultimate strength of that material. So using that we can estimate the endurance limit for different materials. So that is the approximate estimation. And coming to the relationship between endurance limit and ultimate strength. So here, so this gives the fatigue strength to the tensile strength for steel. So as I stated, so this is the sigma E dash is the endurance strength for standard specimen. So we can take the relation with respect of the ultimate strength. So this is for steels. So it is not possible to find the endurance strength for all the materials by conducting the test, so which will induce us, which will incur a greater cost as well as affects the time. Duration is one of the limitation in the fatigue test, so to find out the endurance strength for the each and every material, so that you can come up with an approximate estimation that gives the relation between the ultimate strength to the endurance strength of the test specimen. So that for the steel materials, you can take half of the ultimate strength as an endurance strength, that is uses sigma E dash, that is the actual sigma E dash is the endurance strength for the standard specimen to the half the value of ultimate strength, that is 0.5 into sigma E D. Similarly for cast iron, so this will be taken as sigma E dash as 0.4 into ultimate strength, and similarly for aluminium is as 0.4 times of ultimate strength, and for the copper alloys it is also taken as 0.4. For cast iron as well as aluminium and copper, we can take ultimate endurance strength as 140% of the ultimate strength, but for steels we can consider it as a 50% of ultimate strength. So that gives the proportionate values with respect of the ultimate strength to the endurance strength values. Clear? So in next class we can discuss how the machine components are going to design when it is subjected to the fluctuating loads. That is a design for fluctuating stresses. So we are having the criteria, three different criteria, like Soderberg line, Goodman's line, and Gerber curve. So that will how these can be use the relation with respect of endurance strength as well as the yield strength and ultimate strength, that we will discuss in next class. Thank you. Fluctuating stresses, when the machine component subjected to fluctuating type of stresses, there is a two components that we know that. So one is the mean stress and the other one is the variable stress or stress amplitude, that is sigma. So here, so we can plot a graph. So the failure points of the fatigue test made with the different steels and the combination mean stresses and variable stresses, we are going to plot in a curve. So here on the x-axis we can take mean stress, that is denoted by sigma m. On y-axis there is an alternative stress, that is a sigma A or sigma B. So we can denote A or B. So here, if the mean stress is, that is a variable stress is 0, there is no stress amplitude, which means there is no stress amplitude in the sense, so it is a static load. So in that particular condition, when the stress amplitude is 0, so that is at this point, so stress amplitude is 0, so the design criteria that the strength we consider is the yield strength and ultimate strength. So we can we can note the values of sigma y as well as the ultimate strength sigma u. So on x-axis, that is on mean stress line. So if the variable stress is 0, then the design is completely based on yield strength and ultimate strength point. So that we can note down the values of sigma y, or I can point out the strength values of sigma y and sigma u. So why? Because the stress amplitude is 0, that is the total design is based on yield strength or ultimate strength in case of brittle materials. And coming to the mean stress, if case the mean stress is 0, so if there is no mean stress, so which means for mean stress is 0 in a sense, so it is a completely reversed stress. So that is a reversed stress. For that the mean stress is 0. So the stress amplitude is equal to the maximum stress induced in the component. That is the stress amplitude is equal to maximum stress. So sigma is maximum. In that case, so to avoid the fatigue failure, the design is based on the endurance strength. So here sigma e, you can note down the value of sigma e here, that is the endurance strength on a y-axis when the machine member is subjected to the completely reversed stress, that is the mean stress is 0. So here, by noting down all the failure points by means of the application of the combination of mean stress and as well as the variable stress. So in the point, so if it is an actual, so that is a variable stress is 0, the design criteria is yield strength and ultimate strength. If the mean stress is 0, the design criteria is endurance strength. But when the machine component is subjected to both the components of stresses, that is the mean stress as well as the stress amplitude or variable stress, here there is a different points of failure points can be noted on the graph here. So here, by obtaining different failure points that are plotted here, so the combination of mean stress and variable stresses, so all these pink dots represents the failure points. So here, so by means of the average values of these failure points, we can join a curve between ultimate strength to the endurance strength, and these criteria, you can plot a graph, you can plot a curve, or you can draw a curve from endurance strength to the ultimate strength, that the criteria we call it as Gerber curve. Clear? So we call it as Gerber curve. Similarly, so you can observe there is many of the points that will fall under the scattering of these failure points can fall under the region of this curve. So that the reason, so we can go with another criteria which joins the endurance strength to the ultimate strength by means of a straight line instead of a curve. So that the straight line we call it as Goodman's line. Clear? So first one is so through these scattered failure points, you can join an endurance strength to ultimate strength by means of curve. We call it as a Gerber curve. So even though there is a failure points can be fall under this region, so that so they can observe all these scattered points, so that you can form another line here that joins endurance strength to the ultimate strength. So that the line we call it as Goodman's line. And if you can join the points of yield strength on x-axis as well as yield strength on y-axis, which will show the yield line, we call it as yield line it is. So it will use the first cycle of yielding, so it does not require to fail in yielding, so that so we can gives rise to the another failure or another criteria which joins endurance strength to the yield point. So this is the line we call it as Soderberg line. So even though it can not considering, so this is the two criteria we consider only ultimate strength, but here there is another region that will fall under these values, so which will come to the yielding of failure. So we can avoid that, we can join endurance strength to the yield point strength. So that the criteria we call it as Soderberg line criteria. So here we are having the three different criteria. One is a Gerber curve, Goodman's line and Soderberg line. So Gerber curve is a curve which joins endurance strength to the ultimate strength, and the Goodman's line which joins endurance strength to the ultimate strength, and the Soderberg line joins endurance strength to the yield strength. These are the three different criteria we can use for the design of components subject to the both combination of mean stress as well as the stress amplitude, that is the cyclic loading conditions. Here, so here Soderberg line as well as the Goodman's line are two straight lines here. So using the straight line equation, we can give the design. So for that, let us see the equation for that. So it is a Goodman's line which can join ultimate strength to the endurance limit sigma e here. So which will forms the stress failure stress line. But in order to get the safe region for that, I can provide a factor of safety to that. So we can form the parallel line to that, that is a CD. So we can consider the design point on the CD, so which will use the PQ. So we can consider the PQ as a variable stress, and the PR is a mean stress for design point of P. So now considering the two similar triangles, PQD as well as OCD, so we can write the equations for the Goodman's line criteria. And this is so we can consider this OCD, that is COD or PQD. So from that we can write the equations. So we can write PQ by CY equal to QD by OD. So this QD can be written as OD minus OQ. So that means 1 minus OQ minus 1 minus OQ by OD. From that we can write this equation sigma V, that is sigma E or sigma V by sigma E by factor of safety 1 minus sigma F by sigma U by factor of safety we consider. And finally we will get a straight line equation for that, sigma M by sigma U plus sigma V by sigma equal to 1 by factor of safety. By getting the simplification of above equation, you will get the straight line equation for the Goodman's line. Similarly for the Soderberg line, we can also get the values instead of the sigma U here. So we will get a sigma M by sigma Y. Why? Because the line joins endurance strength to the yield strength, sigma Y by sigma E equal to 1 by factor of safety for Soderberg line method. So the procedure is same for that. Both the lines are straight line equations. So using the straight line equations, you can get the values for that. So here comparing to the Soderberg line as well as the Goodman's line. So Gerber curve is a parabolic curve equation which will have the little complexity in order to solve the equations. So rather than so compared with the straight line equation, as well as so Gerber curve. So there is a possibility of failure. There is many of the failure points scattered below this region, so that this Goodman's line gives a very good results compared to the Gerber's curve. So that preferably go with the Goodman's line rather than the Goodman's line rather than the Gerber curve. So it is a Soderberg line equation as well as Goodman line equation. Again, you can see Soderberg line which can joins from endurance strength to the yield strength, which gives us a failure line. And again, you can consider a factor of safety here. You get another parallel line and consider a design point on this. So we get the relation of sigma M by sigma Y plus sigma V by sigma E equal to 1 by factor of safety, which is the straight line equation, by considering the design point on the safe line P and consider two similar triangles PQD as well as OCD. So you will get an equation of sigma M by sigma Y plus sigma V by sigma E equal to 1 by factor of safety for Soderberg line equation. So and coming to these all these three equations you can observe here. So this is the combination of Soderberg line, Goodman's line and Gerber curve. So and this is the yield line point, that is the first line, first cycle of yielding, we can call it as. So there is always a failure point will be lies below these curve. There is a Gerber curve or Gerber line here, so that we will obtain another straight line joins the endurance strength to the ultimate strength. And here we can observe all the equations for that Goodman's line that gives a sigma m by sigma y. So it is not. So this is a Swartenberg line method, and this is for Goodman's line method. So sigma m by sigma y plus sigma a by sigma equal to 1, and we can consider factors that you will get 1 by FOS here. And similarly with sigma m by ultimate strength for Goodman's line, so that equals sigma a by sigma equal to 1 by FOS. And this is the Goodman's line parabolic equation, sigma e b by sigma e plus sigma m square by sigma u square, so that equal to 1 by factors. So out of these you can use the majority, so you can go with the Goodman's line rather than the sort of Gerber's line. So that is so many of the cases you can go with the Goodman's line equation, which is best suitable for the design of components made of ductile or brittle materials. But the reason one of the backdrop or one of the drawback can be observed in the Goodman's line. Why? Because the line that joins from endurance strength to the ultimate strength, these criteria does not consider the material should fall under the region of the yield. So if the endurance, the stress amplitude is very low with the maximum mean stress values, there is a chance of failure of the components. So in the region of yielding, even if it is not failing in the fatigue, so but it can take care of the fatigue failure, but it is going to be fail in the yielding. So that there is a chance, there is a requirement to modify the Goodman's line, so that we can go with the another criteria is called the modified Goodman's line. So here this modified Goodman's line criteria can be divided for two different cases. So one is for axial and bending loads, and another for the torsional shear stress loads or shear loads. So that so we can have the two different diagrams that can be proposed for the modified Goodman's line corresponding to the axial and bending loads, and one for the torsional shear loads. So this is a fluctuating stress Goodman's slightly modified account for the yielding failure of the component, especially at higher values of stress amplitude. Higher values of mean stress. So with the minimum value of stress amplitude, with the higher values of mean stress, these can be chances of failure in yield. So first of all, we can go with the axial and bending stress. So this is the line. So that is the axial stress and bending stress. First of all, we can draw yield line here, that is which use the obviously 45 degrees, the yield strength of y-axis and x-axis. You can join an yield line. So here, so this is an actual line which can join actual Goodman's line, which can join endurance strength to the ultimate strength here. But with the maximum value of mean stress, the failure can occur in this region by means of yielding, even though it is not failing fatigue. So that the reason this Goodman's line can be intersection point with respect of the yield line. So there is an intersection point with the Goodman's line to the yield line at point B, so that the line can be modified from A to B, as well as from, instead of joining B to F, we can join B to C. So that is now the new line that gives the new region that uses the safe region for the design under the values of Goodman's line. So this is the region of OA. BC gives the new region of safety for design of components subject to fluctuating loads before the yielding of the components. There is only applicable for axial or bending stresses. But when the component subject to the torsional loads, so the graph maybe it differs. So it gives it can be noted that so there is no change in the mean stress values. There is no effect of mean stress with respect of the variable stress up to some extent. So we can observe up to this extent of mean stress, there is no effect on the stress amplitude here, so that all the failure regions will lie at here, so that I can draw a parallel line with respect of the mean stress up to the yield line. So this is the yield line, so this is the yield line point. So you can draw a parallel line up to the yield line, then joins this line to the yield stress instead of ultimate stress point. So now the new region of safety that gives OABC again. So this is the region. So instead of joining this line here, so we can draw a parallel line to the mean stress up to the intersection of yield stress line or yield line, so that we can get a new modified Goodman's line for the torsional shear stress. So these are the two different modified Goodman's line. One is for actual bending, actual as well as the bending stress. One is for torsional shear stress. So here we can reckon how max equals in the factors in here. So we can have the values here, static failure equations. So these are the different criteria you can consider for the design for fluctuating loads. So majorly you can go with the Gerber's line, Goodman's line and Swaderberg line. So out of which so we can use the Goodman's and Swaderberg line, and the Goodman's gives the best results for both ductile and brittle materials, and which requires the need correction. So we can go with the correction in order to avoid the failure in yielding. So that by using the yield line, the intersection of yield line point, you can join the line to the directly to the yield line instead of the ultimate line. It can be separated for the both the yield stress, for the axial and bending stress as well as the torsional shear stress. Clear? So this is the modified Goodman's line. So in the very next class we can see so the combination of these stresses, that is the criteria of Goodman's and Swaderberg lines, which can be applicable for the combined loading condition. So we can consider this is only for single loading condition. So that is we can go with the combined loading, that is when subjected to the fluctuating normal stress and fluctuating shear stress, and how the equations are going to be. And furthermore, we can apply all these criteria within some of the example problems in the very next class. Thank you.